Hey guys, I wanted to go over or show you some examples of how we can use Newton's second law to solve problems involving forces. So let's say, right, and this is going to kind of be based off of the net force practice. So let's say we have a force F acting on mass m with acceleration a. Right. What is the acceleration? Mass is 1/2 m. Okay. So this is kind of like those if-then statements, right? If I 1/2 the mass, then how does the acceleration change? So from Newton's second law, we know that acceleration is equal to net force over mass. And since I'm only comparing mass and acceleration here, I can ignore this net force part. And I can say, okay, well, acceleration then is proportional to 1/m. So acceleration is proportional to, well, I'm halving the mass, so I'm going to plug in a half for mass. 1 divided by 1/2 is actually 2, so that means I'm going to get twice the acceleration if I halve the mass. But what if we have a combination one? What if it's the same sort of thing, but what is the acceleration if there is 4F, like 4 times the force applied, and, I don't know, 8 times the mass? Well, I'm going to start with the equation. A is equal to net force over m. And I'm comparing both net force and mass and acceleration. So I'm going to keep everything, change it into a proportionality, because it's not going to be exactly equal. Force changes by a factor of 4, so I'm going to plug in a 4 for force. Mass changes by a factor of 8, so I'm going to plug in an 8 for m. And then I can simplify that to 1/2. So that means I'm going to get half the acceleration, or 1/2 a. So those are kind of like those if-then questions. Okay. Now we can sort of do like a basic net force question. So let's say a box is pushed with 10 newtons of force, experiences 2 newtons of friction, and has a mass of 2 kilograms. So the first thing we're going to do, of course, is draw a free body diagram. This object is going to have a force of gravity and a normal force, because it is going to be on a surface if there's friction. Then we have the applied force, which I know is 10 newtons, and a friction force, which I know is 2 newtons. Then I'm going to do net force equations in the x and y direction. The y direction is not moving, so I have a net force of 0. So that tells me that normal force minus the force of gravity is 0. And in the x direction, we are likely accelerating, so I have ma. It doesn't say I'm at rest or moving at a constant velocity. So I have the applied force minus the friction force, ma. So let's say we were solving for that acceleration. I would do the applied force minus the friction force divided by the mass is my acceleration. So 10 newtons minus 2 newtons over 2 kilograms. This is 8. So 8 divided by 2 is going to give me 4 meters per second squared. Now, this is a pretty common question. Sometimes you're given the force of friction. Sometimes instead you're given the coefficient of friction, like maybe the coefficient of friction is 0.2. Right? We could then find the force of friction by using our kinetic force of friction equation, which is the coefficient times the normal force. So let's say that this was this example here and we didn't know that force of friction. I could calculate the force of friction by doing 0.2. The normal force I know from the y direction has to equal the force of gravity. The force of gravity is equal to mg, so 2 kilograms. G is 10 newtons per kilogram, so times 20 newtons. And that gives me a value, 0.2 is 1/5, so that should give me 4 newtons. So then I could find my acceleration, applied force minus friction over mass. So 10 newtons minus 4 newtons now over 2 kilograms. And now I have an acceleration of 3 meters per second squared. Don't forget, unless the question says the object is already moving, we do have to make sure that the object will move, right? So just as a reminder, those will it move questions, you want to see, is the applied force greater than that maximum static friction force, which we can calculate by doing the coefficient of friction times the normal force. Okay? But sometimes it tells us the object is already moving. Let's just do a quick something at an angle. So maybe I have a person pushing on a lawnmower, right? So when you push a lawnmower, you kind of push down on the lawnmower and at an angle. So hence that downward force at an angle. A, G, and it's a lawnmower, so there's going to be friction, kinetic friction, because we're sliding. Okay, so I notice that my applied force is at an angle, so I'm going to draw another diagram with my forces drawn in, not necessarily to scale, but just so I have them to reference. Because this is going to make drawing or creating my net force equations much easier, because I see in the x direction I have only 2 forces. And I'm not necessarily moving at a constant velocity, so I'll say my net force is equal to ma. But I do know that it's got to be the x component of the applied force minus friction equals ma. And then in the y direction, I have 3 forces, and those 3 forces have to combine. And vertically, I am at rest. It would be very terrifying if vertically this lawnmower was not at rest, because that means it's coming off the ground and showing the blades. That's scary. So I have a normal force upwards, a y component downwards, and a force of gravity downwards equals 0. Now my x and y components, we know how to find those. Those are the triangles. Right, let's say this is at an angle theta. Right, here's my y component on that triangle. Here's my x component. Here's my applied force, here's my angle, and as long as we're dealing with this angle in here, the angle with horizontal, we can shortcut to the applied force in the y direction is Fa sine theta. In the x direction, it is Fa cosine theta. So now that I know those, that's how I calculate my components, I could plug that in. So Fa cosine theta minus force of friction is ma, and I know that my normal force minus Fa sine theta minus Fg is 0. So let's say this question actually wanted us to find what is that coefficient of friction. Okay, so let's say this applied force is 200 newtons, and this object has a mass 5 kilograms, and this angle is 30 degrees. Okay. And the acceleration is 1 meter per second squared. Okay. We're accelerating pretty slowly. So my whole goal is to figure out what is the coefficient of friction, and to find the coefficient of friction, I need the force of friction. So I'm going to solve for the force of friction. So 200, well, let me rearrange for friction first. So Fa cosine theta minus ma is the force of kinetic friction. So 200 newtons, cosine 30 minus 5 kilograms times 1 meter per second squared. Right, so we got a force of friction that is 168 newtons. I have the force of friction, but I still need the coefficient of friction. There's a difference. So I'm going to find the coefficient of friction by using the equation that has it in it, or that force of friction equation. So the coefficient should be the force of kinetic friction over the normal force. I have the force of kinetic friction, it's 168 newtons, so it looks like I need to know the normal force. So now I'm going to come back over here to find the normal force, which is going to be the force of gravity plus Fa sine theta. So force of gravity is found by doing mg. So now I can substitute in 5 kilograms times 10 newtons per kilogram plus 200 newtons times the sine of 30. So that's 50 plus 200 sine 30. And that gives me a normal force of 150. So based on the numbers I gave, it's 1.12 newtons. Now you might remember I said that the coefficient in our classroom is usually going to be less than 1. That is the truth. I just made these numbers up off the top of my head, which is why we're getting a really big coefficient of friction. Okay, so that's why the numbers aren't necessarily working out. Now, even with Newton's second law, we're going to follow the same problem-solving process that we did when we had a net force of 0, free body diagram, draw the components, do the net force equations. As long as you're following that kind of thought process, you should be good. You should be able to solve.